screen share. Okay, so for case one, I remember I did the first collision with you guys, and that's what I got. Remember, both masses were the same for case one, collision one. Cart one was going 6 meters per second to the right. The other car was going -3 meters per second to the left. So those are the velocities that were recorded. So the momentums were -3 and 6, respectively, and so total momentum was 3, so it was conserved. And the energy that we got was 1/2 mv squared. So you're doing 1/2 times 1 times -3 squared, so you got 4.5 and 18. So it looks like there's just a switch there. Total kinetic energy is also conserved. If you change the mass of the first cart, but also drop its velocity by half of what it was originally, but keep everything the same for the second cart, these were the velocities I got, -1 and 5. The momentums will be -2 and 5, respectively, so total momentum stays the same. By doing 1/2 mv squared, so 1/2 times 2 times -1 squared, I got 1. 1/2 times 1 times 5 squared, I got 12.5. But still, the total kinetic energy stays the same at 13.5 joules. So that's what happened for case one. Hopefully you guys got that for that one there. Let's go to case two. Let me rotate this. For case two, those were going completely inelastic. However, so it means they stick together. However, the velocities, so the velocities did drop, obviously, 1.5, 1.5. You could combine the two momentums because they kind of count as one body. So you could have said that for the final momentum, you had like one body with a mass of 2 kilograms and a velocity of 1.5, or you just do them separately. Do 1.5, 1.5, because they do give them to you. So if I run that simulation right here, reset, so they stick. So they do say they're 1.5 each. So I guess you could do that. But the total momentum stays the same. Likewise, if you doubled the mass of the first cart, but took half of the original velocity of the first cart, the initial velocity, final velocity are 1 and 1, but the momentums are 2 and 1, you still get 3, so it still stays the same. Where it gets interesting, the kinetic energy drops significantly. So if you were to calculate the kinetic energy in 1/2 mv squared for each of these, you get 1.125, 1.125. The square of 1.5 is 2.25, you got to take half of it. Or if you do it for 1/2 mv squared for this one, you get 1 and you get 0.5, if I'm not mistaken. And so again, we do see a huge drop in their total kinetic energies. And I'm actually kind of curious about that ratio. Let's see if I were to compute it. So it looks like it's about 11.1%. Yeah, so it's kind of interesting. So the total kinetic energy comes down to about 1/9 of what was previously. So that is pretty consistent. So I think that is kind of interesting that what we're noticing there. So again, let me get my stylus out. If you do 2.5, and also if you do 1.5, so it's kind of interesting that we're seeing that phenomenon happen. Some is kind of interesting. So we'll keep that in mind. So in case 3. So this is what I got. Now, if you guys didn't get that, please let me know. But if I run through the simulation again, So reset, make that 0.8, and hit play. So you kind of see that's what happens there. But if I were to double this mass and have that velocity, run again, oops, let me reset that. Yeah, you get that. So going back to my work here, those are the values I had. If you calculate the momentums, it's still conserved. But the kinetic energies do change. And I think I did that right, but if you guys got something different, please let me know. And if I do calculate the ratios between the new kinetic energy divided by the initial, let's see here. So you get 0.676. Yeah, I kind of get the same thing. Yeah, I get about 0.68. I think I ran a little too soon, but so it's kind of interesting that we're seeing the same ratio. So there might be some relationship here with elasticity and what and how much is lost to friction. So we'll probably explore later this week. I'm going to clear that. And something else. And so obviously for all three cases, momentum is conserved. Explain answers above using data and calculation. You could just make a statement here like, the potential energy, the momentum was consistently 3, regardless of whether we, or just stayed the same before and after, regardless if we change the mass or the velocity. And then you could kind of talk about, even if we change elasticity, we also notice it was also the same. So you don't really have to say too much about that, I suppose. And expand the bar graphs and at least one graph on the simulation support your answers above. Well, if you take a look at it again on the simulation, you can kind of see how there's kind of a trade-off, right? So the transfer is pretty much the magnitude of these two. So the transfer goes this way, goes that way. Even though those are different, this stays the same the whole time. So there's no change in momentum whatsoever. So bar graphs kind of confirm that. So again, I guess you could say how you see that the transfer goes in equal opposite directions for carts 1 and 2. And the transfer is essentially the magnitude of the blue and the green bars. And then if you take the difference between this bar and this bar, you get this. Difference between this bar and this bar, you get this. So that's the momentum of your system. So the bars kind of are a nice visual representation of the conservation of momentum. For energy, of course, they were different. For case 1, it was conserved, but not for cases 2 and 3. And again, you can kind of explain, kind of just show like, yeah, when we calculate the energies, they're different. Talk about how it's, for case 2 is 1/9. The final kinetic energy is 1/9 of the initial kinetic energy. Case 3, you could say is about like 0.68 or so. What you could do is you can change the graph. So let's run this again. So you do see the energies kind of change somewhat, but if I kept the elasticity at 1, So it looks like you have roughly 8 and 4. That's up to 12. You get the same thing here. Let's just do this. Let's play it that way. Yeah, again, you see that they kind of all stay the same. But if I do this, you see the total connection drops by quite a bit. Or if I do this, again, the total kinetic energy goes down by a fraction. So you can kind of see that graphically it's also confirmed as well. And describe and explain the difference kinetic after the collision between these three cases. Again, that's where you can probably talk about the whole fraction bit, like the final kinetic, the final kinetic energy is 1/9 of the initial for case 2 when it was completely inelastic. When it was a portion that was inelastic, then that was about 0.68. So you can kind of get into that stuff too. So the rest of this we'll explore tomorrow. I think that would be good to do. So hopefully you guys got everything through up to page 4. Let me go ahead and briefly talk about what we're going to talk about tomorrow, which is on Hooke's law. And maybe I'll do like one of the examples here on springs. Not sure if we'll get too deep into all this. We could probably, so I'll give you guys a video on springs tonight. I think that would be good. And maybe a little bit on waves just to kind of reinforce what we talked about today. Let me get the actually solution key here for that one. Any questions about the lab? No? Okay, cool. One sec here. Somewhere else. One sec. Okay. So, Hooke's law is right here. So again, this should be under the week 5 problem sets, I believe. So 7.2 on Hooke's law. So this is a formula that we use. F is called the restoring force. X is going to be the distance the spring goes back. So say I kind of just drew this again, but drew it kind of like this here. So wherever, and say you have like a ball at the end here. So X is the distance actually you bring the spring back. So we'll say now it's tighter. So you apply some force. That's what we're calling X. And K is called spring constant. Some springs are more firm than others, right? Kind of like your bed, right? Your bed has springs in it, and some people like a very firm mattress, some people don't. And so a lot of that, or if you have like Sleep Number, that's what it's doing. It's actually adjusting the coils. So some people like more firm, some people don't. So that's kind of what K is. It's kind of indicative of the stiffness or firmness of the spring. Force will pull the mass backward towards equilibrium. So equilibrium is kind of like when you're like kind of at that happy balance when the spring is just kind of like laid out and it's not really moving or not going back and forth. As mass gets to equilibrium, it has momentum So it continues past. I think what's meant by that is I believe if you pull on it, it's going to move and it'll have momentum. I think that's what's meant. I'm not 100% sure that third bullet point means. Let's talk about energy. So the force acts over distance, work is done. And here's the formula for the potential energy of a spring, 1/2 kx squared, because there's that potential for a spring to do work. And again, k is a constant and x is a distance that the spring travels. So let's say you have a Nerf dart gun that uses a spring to launch a dart. If you take 24 newtons of force to compress it 6 centimeters, what is the spring constant? So first of all, force equals negative kx. So you do 24 for your force, and then k, and because it's you're compressing it, it means your x is negative. Because what's happening, it's going to the left, which we consider to be the negative direction. So we'll say negative. And remember, you have to do it in meters, because units in meters. If we solve for k correctly, the units we call a newton per meter. So that's the spring constant. And if you want the potential energy, about EL stands for elastic potential energy. You're doing 1/2 times a constant, which is 400, times the distance traveled squared. And then you should get about 0.72 joules. You did that correctly. So that's a calculation that we'd have for that. Let me talk about the speed of a wave on a string just really quickly. And I think we'll kind of end it there for today because I don't want to get into some harmonic motion. I think I want you guys watch a video on it and then we'll talk about it tomorrow. And we do 7.2 and then more of the lab tomorrow as well. So again, we're going really light this week. I'm going to go and clear this. So speed. I'm not sure what's meant by the first bullet point here. But the speed of a wave depends on the medium. And medium means like what it passes through, for example, air, water, etc. And so certain mediums can slow it down. And sometimes if the air has pollution or other stuff going on, that could also impact it. For string speed depends on the tension of this that we have with the string. And linear density, which is defined as mass per length. And if you think about the units here, and F is force, of course. So remember, that's a Newton over kilogram per meter. Remember, Newton's a kilogram and if you flip that, those cancel. And you get meters per second. So the units make sense. But that's another form that we'll be using. I think what's meant by the bullet point above, on a string if one part of the string is pulled up, the other is pulled down. So I guess if you have like a piece of string connected to a wall, and so if one's pulled up, the next piece I'm not really sure. I need to think about this one. So we'll just end it there for today because it's almost 1:30. Not sure what's going on with that one there. But anyway, the formulas we have, and we'll do some work with this tomorrow. So I will put the discussion topic later today. I'll have that up very shortly. And I'll also have the video in Google Forms. So I'll have all that done by 2 o'clock. That's the plan. And then we'll meet tomorrow morning. And again, tomorrow we'll do more work with this. I think I'll probably maybe do some on pendulums because that's kind of related to this stuff. And we'll do more of the lab. And then I think Wednesday we'll do some stuff on, a little bit of stuff on rotation or centripetal motion. I think that will be important. And Thursday, I'm still deciding what I want to do. I don't think I want to do a test, but we'll figure it out. Okay, I think we're all done for today.
Thank you.
Yep, and I'll stop the recording.